Good day, my name is Stein. I'm your lecturer for Mechanics of Machines 3. I would like to discuss the first chapter with you, and that will be the construction of velocity and acceleration diagrams. First, I'm going to do some theory with you, and after that I will do a typical problem on the board, how to construct the velocity and also the acceleration diagrams. For your velocity and acceleration diagrams, you need drawing instruments like a compass, protractor, ruler, a scale ruler, a rubber and a set square, especially as big as possible. With previous work in mechanics, you developed the relationships covering the displacement, velocity and acceleration of points as they moved along straight or curved paths. We are going to use these same relationships but must also account for the rotational motion of the body as well. Thus, it involves both linear and angular quantities. You already know that to accelerate a particle of mass requires a force, and to accelerate large pieces of mass such as links assembled from a mechanism also requires that a force or forces be applied. Forces must be present in systems which have mass and which accelerate. Newton's second law of motions tells us that. This law states that force is proportional to acceleration, and this means that more acceleration requires more force. So if a mechanism is constrained to move in such a manner that causes large accelerations, then large forces will be carried by at least some of the components. Hence, you can see that forces are present in mechanisms which move and accelerate, and therefore with your design you must make sure that all components are capable of carrying the forces to which they are subjected reliable and without failure. Let us look at some definitions. Like a machine is a mechanism or an assemblage of mechanisms which are arranged in such a manner that energy may be transferred from a supply in order that work may be done. Mechanism consists of two or more links, one of which must be fixed and which are connected in such a manner that the movement of one link induces a definite movement in the other links. And what is a link? Is one part of a machine which has motion with respect to another part of the machine. A mechanism is used to produce mechanical transformations in a machine. This transformation could be any of the following. It may convert one speed to another speed. It may convert force into torque or torque into force. It may convert angular motion into linear motion. It may convert linear motion into angular motion. It may convert one force to another force. It may convert one torque to another torque. For example, let's look at a simple crank piston system. This is the piston, the conrod, the crank arm. Gas pressure on the piston forces it sidewards here, pushing on the connecting rod, in turn pushes on the crankshaft, causes it to rotate. There is the crankshaft arm, then it will rotate. The force on the piston is converted into torque. So do you have force here and you convert it to torque. Let's look at typical engine in a vehicle. You get the block, and then you get the crankshaft, the conrods, the pistons, the flywheel. All these parts are connected to the block. And for the construction of the velocity acceleration diagrams, we take the block as the base. Or if every part here is connected one or the other way to the block. The following diagram shows a space diagram of a mechanism with its velocity and acceleration diagrams. So your mechanism, first what you're going to do is you're going to draw a line diagram, or also called the space diagram of your mechanism. at a specific position. From your space diagram, you're going to construct your velocity diagram. You get information from your velocity diagram to construct your acceleration diagram. The reason for constructing your velocity and also the acceleration diagram is to do some calculations and see the force or the torque act on that specific link. If you can go back to your standard Newton's second law, Fa equals to ma. This is for linear motion. For angular motions, you get your effective torque equals to inertia times alpha, angular acceleration. You can calculate the inertia of that specific link. By the construction of the velocity and acceleration diagram, you can you find the acceleration, angular acceleration. Then you can go and work the torque, act on that specific link. Then you can go back to your drawing board. With strength of materials, you can redesign that specific link if there's a failure in the industry. It's easy to just replace the link with a bigger or stronger type of material, but that can lead to other problems. So with your velocity acceleration diagrams, you determine the force or the torque act on the link. With the strength of materials, you go to back to your drawing board and you do a redesign. Some methods to do these calculations is a cross product, mathematically difficult because it's going to take a long time to do a more advanced type of mechanism. So we're going to concentrate on a graphical method, velocity and acceleration diagrams. Your graphical method consists out of, as I mentioned, a space diagram or line diagram. You're going to construct that according to a specific scale in the links in a specific position. From that, you're going to construct first the velocity diagram, also according to a scale, and you must work accurate. Get information from your velocity diagram, and then you're going to construct the acceleration diagram, also according to a specific scale. All three diagrams must be drawn accurate with your drawing instruments. You must, as I mentioned, you must draw according to a scale, and also just remember, the bigger the scale, the smaller the error. Let's start with your velocity diagrams. Deals with the study of relative motion between the parts of a machine. These relative motions of the links of a kinematic chain are completely constant. The displacement of one link brings about corresponding displacements of all the other links. Any point on any link of a mechanism is therefore compelled to follow a definite path. Hence there is displacement, and these displacements are dependent on time from which the velocity of the point can be determined. The velocity of such a point can be found by means of two graphical methods. Velocity diagrams, instantaneous center method. You're going to concentrate on both that two methods. If a link rotates about a fixed axis, then any point on that link has a linear velocity and an angular velocity. Let us start with this mechanism. First thing, we must see how many links are in your mechanism. We count the fixed point. As I mentioned, the block of that engine form the base. So all that other links is connected to the base. It will be then that point O, point F, and point C. That counts as one link. Then the second link will be OA, then AB, then BC, and then DE. And E is also a piston, a sliding block. Restrict to move on a vertical axis. So how many links are in this mechanism? Is 1, 2, 3, 4, 5, 6. That is a 6-link mechanism. Starting with the velocity diagram. First thing to do is go and stand on point O. Observe A. They will tell you in which direction is rotation. For this example, let's take clockwise. The direction of rotation clockwise. Now, they will give you a rotational speed. I will take this one 96 rests per minute. First thing to do, they gave you the rotational speed of that link, the direction, and the rotation speed in rests per minute. So change it to angular velocity. So you know angular velocity equals to rotational speed in rests per minute times 2 pi divided by 60. And for this rotational speed of 96 will give you 10,1 radians per second. So go and stand on O. Observe A. If you take your drawing instruments, that motion will be perpendicular to link OA. So what do we have here? We do have the velocity of A relative to O. We can calculate the magnitude. That will be omega times the length of that link. Let's take the link 1 meter. So that will give you your linear velocity equals to your angular velocity times a radius. And that will be the length of link OA. So let's take it 10 meters per second. So we do have a vector here. It's got the magnitude and a specific direction. You can't change the magnitude or your direction. Your velocity diagram. The center here will be the base of that mechanism. So this will be O, the center, no? F and C will be the center of your velocity diagrams. Okay, according to a scale, no? Take the scale 20 millimeters equals to 1 meters per second. So that will give you 200 millimeters length of that link. Let's go back to this direction. Stand on O, observe A. You do have the direction and you can calculate the magnitude. That will be your a vector now. It's got the direction and it's got the magnitude. So from the center, because we stand on O, observe A. So from O, we draw in that vector. Let us do it the other way. Use a construction line. No? And now you've got the direction. Work through a scale. I took it as 20 millimeters equals to 1 meters per second. So 20 times 10, that gives me 200 millimeters. So measure that length from that center, 200 millimeters. So that plots A on your acceleration diagram. And you can also darken that line. As we darken that line, nah, with the length from the scale and the magnitude, so that plots A on my velocity diagram. So we this line is perpendicular to that link OA. So we plotted A. Now we can go and stand on A and observe B. We only know the direction. The direction will be perpendicular to that link. But we do not know what the magnitude of that velocity vector, but we know the direction. So a line perpendicular to AB through A. Okay, we will make it. Just learn to use your drawing instruments, né? Draw a construction line. Somewhere on this line, we can plot B. And that is as far as we can go from this side. But we do have C on our velocity diagram. Therefore, go and stand on C, observe B. And we only know the direction. The direction will be perpendicular to link BC. Therefore, through C, draw that line perpendicular to, draw the line, and where they intersect, that two lines, plots B on your velocity diagram. So we can darken this line. All right. The next will be to go and plot D on my velocity diagram. We can see on our velocity, on our space diagram, A, D, and B is on one link. So where is A? There's A, no? There's B. So somewhere in between, we can plot D. Use ratios. For the purpose of this one, let's make AD, the length of AD equals to the length of DB. So exactly in the middle of this line, we can plot D. So with this, we plotted D. Now you can go and stand on D, and you can observe the sliding block E. Ignore your motion, your movement. Né? Only concentrate on the possible motion of E relative to D. And again, it will be perpendicular to that link. That will be the possible motion of E relative to D. So through D, we can draw that line. We construct, again, a construction line. And so somewhere on this line, we can plot E. But we know E is moving, is restricted to move only on the vertical axis. So on the vertical axis of my space diagram, we can plot E. So let's darken these lines. So your velocity diagram is complete. Now, the question, what is the velocity, for example, of E? You can go to your velocity diagram. This is drawn according to scale. You can go and measure this distance, always from your center, from the base. No? Work through your scale, what you choose, and that will be your velocity of E. And that will also be your absolute velocity. For angular velocity, as you know, angular velocity, you need a linear velocity and you need a radius. For example, if I ask you the angular velocity of dE. So where is D? There is D, there is E. If you measure this distance, that will be the relative velocity of D to E. A work through scale will give you that answer. The radius will be the length of link DE. And if you divided that in your velocity, will give you your angular velocity of DE. Okay, now let us start with the acceleration diagram. As you remember, if you do have a link, rotate in a specific direction with a constant angular velocity, it will always have a normal acceleration. The direction of the normal acceleration will always towards the center of rotation. And to calculate your normal acceleration, you need an angular velocity square times a radius. Also, linear velocity divided by r for your normal acceleration. OA is rotating at a constant angular velocity. So there will be a normal acceleration. No tangential acceleration. Remember, tangential acceleration is this one, perpendicular to the link. And that will be your tangential acceleration. And this you need to have your angular acceleration times a radius, for example. So first, let us construct a table. We say this is your link, and then this is your normal acceleration. Starting with link OA. So that will be the linear velocity of A relative to O square divided by the length OA. Will be in meters per second square. Also, you must choose a scale, specific scale, to fit on your paper. Né? I took 2 millimeters equals to 1 meter per second square, for example. Né? Right. The following will be, next one will be link AB. So we need the velocity of A relative to B square divided by length of that link AB. Also, I don't have space here. You do the same with BC, also with DE. Use the same method to calculate the normal acceleration of link BC and DE. Just remember, the accelerations of that link is constant, so it's got only a normal acceleration, no tangential acceleration. But due to the length of all the other links, and the position, will have a normal acceleration as well as a tangential acceleration. Start with link OA. We calculated, we do have a scale. All right, let's start with that one. So that's also acceleration vector. So you can use your drawing instruments. Okay. This length will be the magnitude of, or the magnitude of the normal acceleration of link OA, and also through your scale you can draw in that length. But remember, that line, let's call it a line, must be parallel to link OA. You can't change that direction. That is important. All right, so that plots A on my acceleration diagram. Take note of the footnote. 1, that means I plotted A on my acceleration diagram. Again, here is my base. It will be O, it will be F, also it will be C. The next will be to go and stand on A. Stand on A, observe B. It has a normal acceleration towards you. Because this is now the center of rotation for link AB, for the purpose of constructing the acceleration diagram. Therefore, it will be towards you. We stood on A. So a line parallel to AB. Where is AB? That line, that one. One parallel to AB, through A, through the scale, you can draw that vector, acceleration vector. Né? But that is not yet the absolute acceleration of B relative to A. This is only the normal acceleration. There is still a tangential acceleration. And you can use dotted lines. So somewhere on that dotted line, né, you can plot B. That is as far as we can go from this side. Let's go to C. To plot B, stand on a point where you can see B. And just remember, you can't overlook a link. You can't stand on O, observe B, because you do have A in between. I can't stand on A, observe C, or C, observe A. Only this, you can look on if this is a one solid link, I can stand here and I can look at any place on it because it's solid. No? But if you do have a pivot point, a sore point, you can't overlook that pivot point. Therefore, stand on C, observe B. BC, you calculate the magnitude of the normal acceleration. And that one will be perpendicular, parallel to that link. BC. You do have the magnitude, and you can draw in that one. Eh? So, but there is still a tangential acceleration. We know the magnitude and direction of the normal acceleration. We still need the magnitude of the tangential acceleration. That point, we can name it B relative to C. Also, this one, we can say this one is B relative to A. Now, draw a line perpendicular to BC. I hope I can do it here. Let me see. Yeah. So we do have two lines for B. There's one line, stood on C, observe B, gives you that line. Stand on A, observe B, gives you that line. The intersection there plots B on my acceleration diagram. The next will be to plot D. Similar to what you did on the velocity diagram. Where is B and where is C? This represents B, this represents A. So draw that line, and halfway between that point A and B, we can plot D. Remember to use the same ratios as what you did with the construction of your velocity diagram. The next, go and stand on D, observe E. It's got a centrifugal acceleration towards you. Parallel to link ED. Let me see. Somewhere on that line, we can plot. This is the normal acceleration of E relative to D. You calculated the magnitude, so work through your scale, and you can draw that point. So that point will be E relative to D. Tangential acceleration will be this one. Remember, we use dotted line for the tangential acceleration. And we know E is restricted to accelerate on the vertical axis. So on my vertical axis, you can plot E on your acceleration diagram. Let's darken that line now. Dotted lines, and your acceleration diagram is complete. All right, the directions, also important. We only work with absolute accelerations, velocities. If we use relative velocities, accelerations, that will be only where you do have a slider mechanism, where you deal with the Coriolis component. So for your velocity diagram, always from your fixed point, as you can see here, will be the direction. So according to this, for this moment, E is moving vertical down. Also with your acceleration diagram, there you can see it means E is accelerating vertical down. If you do a construction, for example, and you get E in the opposite direction, it only means it decelerates and not accelerates. And from here you can do your calculations for your angular acceleration.